Welcome to join our session 7B, CODES plus ISSS, the session of intermittent computing. I'm Yunhao Chan, the session chair, and our co-chair is Professor Meng Zhao. She's also here. And in this session, we have 4 talks. The first talk is about stateful neural networks for intermittent systems. And the speaker is Chih-Hsuan Yan. And Chih-Hsuan received the bachelor degree from the Department of Electrical Engineering from National Taiwan University. And he got the master's degree from National Taiwan University in 2017. And he's currently pursuing his PhD degree in information engineering. And he's also a research assistant with the Research Center for Information Technology Information in Academia Sinica, Taipei. And his research interests include embedded systems and intermittent computing. So now please join me in welcoming Dr. Chen. Oh, Dr. Yan, sorry.
Okay, thank
you. So now please share your screen now. Thank you.
Wait a minute. Okay, can you see my screen?
Yes, thank you.
Okay, then let me start my talk. Okay, hello, I'm Chih-Hsuan Yan from Academia Sinica. In this work, we propose the concept of stateful neural networks, which enables a DNN to indicate the inference progress itself when executing under intermittent power. Well, energy harvesting has unlocked new possibilities for sustainable and low-cost batteryless edge devices. However, as ambient energy is weak and unstable, they experience frequent power failures and intermittent operation. Recent work has enabled the execution of deep neural network inference on such intermittent systems, but their execution performance is impacted by the additional overhead required to accumulate the inference progress across power cycles. Therefore, we need to achieve an inference speed on batteryless devices comparable to that on battery-powered devices. Due to resource constraints, both linear and nonlinear layers are processed as tiles. To compute a tile, the components related to the tile input are fetched from non-volatile memory to volatile memory, and the tile output is written back to the NVN. A computation operation may contain multiple sub-operations referred to as jobs. Due to limited NVN capacity, the job outputs written to the NVN buffer may overwrite those written by previous layers. On intermittent systems, an inference may take multiple short power cycles to complete. Upon power failures, the volatile data and the state of the system is lost. Therefore, progress indicators are essential for intermittent inference. They are preserved into NVN during inference with job outputs, which are essentially output features or partial sums. And the preserved progress indicators are used to recover the interrupted inference upon power resumption. The state-of-the-art generate and preserve a progress indicator paired with a job output. The last preserved progress indicator is used to correctly identify the interrupted job that needs to be resumed. Hawaii preserves progress indicators independently of the job outputs, incurring a high progress preservation overhead. In contrast, Japari augments the DNN to allow progress indicators to be preserved simultaneously with job outputs, thereby reducing the related data transfer overhead, but at the cost of extra accelerator computations. These prior efforts incur significant computation and data transfer overheads to separately preserve progress indicators. In fact, we observed that progress preservation overhead accounts for a large portion of the inference latency, and this overhead increases with the gap between the computation and the data transfer overheads. Motivated by this observation, this work presents the first attempt to enable a DNN to indicate the inference progress itself, thus eliminating the progress preservation overhead. Motivated by these observations, we present the concept of stateful deep neural networks, where inference progress information is embedded within the network in the form of inference states. Our runtime middleware embeds state information into the DNN during inference, such that the computed and preserved output features intrinsically contain progress indicators, avoiding the need to preserve them separately. Subsequently, the embedded states are used for correct inference recovery. Realizing stateful DNNs raises two design challenges. The first challenge is where to embed states in the network such that the states and output features are isolated and not corrupted during inference. This is particularly difficult because embedding at embedded locations may cause the state to be lost, or more seriously, compromise the model accuracy. The second challenge is determining what states to embed such that the interrupted inference process can be correctly recovered. This is non-trivial as the same NVN region is reused to preserve job outputs of different network layers, making it difficult to identify the latest preserved job output. We address the first challenge by state information embedding, which determines the position and the representation of the states in the network. The key idea is to split the value range of specific network components to represent different states in such a way that they do not interfere with the job output computation. Therefore, we embed states into each bias for linear layers and into each job output for nonlinear layers, and we split their value ranges into two subranges. We address the second challenge by state information assignment, which ensures the specific assigned states allow the latest preserved job output to be uniquely identified. The key idea is to ensure that the states assigned to the selected network components of the current layer are different from those assigned for the previous layers that reuse the same NVN locations. We evaluate our approach on two Texas Instruments microcontrollers with different computational efficiencies. Experiments were conducted under continuous power as well as under intermittent power with strong and weak power strengths, producing different power interruption rates. We evaluate stateful with three different DNN models with varied levels of complexity, representing those typically used in tiny ML applications. We compare stateful as well against Hawaii as well as Japari, both of which are state-of-the-art intermittent inference techniques. A state information embedding ensures that output features computations are very minimally affected. Stateful does not significantly impact the accuracy of the evaluated models. Compared to the baselines, stateful reduces the progress preservation overhead between 14 and 83% of the inference latency, down to between 1 and 21%. And this proportion of overhead roughly remains the same, regardless of the level of power instability. This enables stateful to speed up intermittent inference by 1.3 to 5 times. Improvements are more obvious when the overhead of baseline approaches are higher, specifically when executing modern convolutional neural networks with larger and wider input feature maps, resulting in more data transfers, and on computationally lightweight devices under weak power. Here, we present a demo video comparing stateful and Japari under intermittent power, executing an image classification DNN. The intermittent system executes using only the harvest energy from the lamp. Runtime information is displayed on the user interface, including the inference progress, status of the power supply, and the progress preservation overhead. Here, we demonstrate that stateful takes less time to complete an inference. This is primarily because stateful neural networks intrinsically contain progress information, thus eliminating the data transfers required for progress indicator preservation. Therefore, compared to Japari, stateful is able to speed up intermittent inference by 2 times on average. To conclude, we present stateful neural networks that enable a network to indicate the inference progress itself. Existing approaches incur excessive overheads as they preserve progress indicators separately from output features. Our approach embeds state information into the network, allowing progress indicators to be intrinsically contained within output features. The specific position and the representation of states ensure output features and states are not corrupted, thus maintaining model accuracy. And the specific embedded state allows the latest output feature to be identified, enabling correct inference recovery. Our approach can speed up intermittent inference by 1.3 to 5 times with negligible accuracy loss compared to 2 recent approaches. Improvements are more noticeable for convolutional neural networks deployed on severely resource-constrained devices, executed under weaker power. Our stateful middleware stack has been made open, simplifying the development of low-latency, intelligent batteryless devices. Thank you for listening. I'm happy to answer any questions, and please visit our poster section for more details.
Okay, thank you very much for your talk. Any question here? Okay, so let me to ask you several questions. My first question is that what are the main challenges and overheads on enabling the stateful design? Because it seems that you need to log or memorize several things that the other words doesn't. Yeah.
Actually, in our approach, we still need to memorize the progress indicators. The difference is that how we memorize the indicators. In previous approaches, the progress indicators are preserved separately. And in our approach, the progress indicators are embedded into output features. So the overhead is eliminated. There are no more data transfer overheads for embedding the progress indicators.
Okay. It seems that Wei-Che have one question, right? Can you speak out for your question?
Yes. Thanks for your talk. And I'm wondering, can this approach be applied to other applications? For example, besides running an inference on intermittent devices, exchanging data among devices is also a common scenario.
Oh, yeah, thanks. That is a good question. In our approach, progress indicators are embedded into output features in deep neural networks. In theory, such an approach can be applied to any data that can tolerate minimal numerical errors. For example, image processing, audio processing, or some kinds of sensor data. If data exchanged among devices have such a property, our approach can be applied as well.
Okay, thank you. I have another follow-up question. Since you mentioned that the log data are embedded with the output feature, and does it mean that your design is not easy to be extended to other AI algorithms, or it is also very easy? Can you have more explanation?
It can be easily extended, but yeah, for other AI algorithms, it needs to be modified so that the states will be embedded. if we need to support other operators like batch normalization or any other more advanced operators, they need to be modified. But the modification is very trivial. We just need to split the value ranges into two subranges and embed the state. That's just a few lines of code.
I see. Thank you. Thank you very much. Because the time limitation, so we need to stop here. Thank you very much. Thank you.
Thank you. Thank you.
So now we need to move to our second talk. Dr. Tsai, can you share your screen?
Yeah, sure.
Okay, thank you. Our second talk is entitled Intermittent-Aware Distributed Concurrency Control, and the speaker is Wei-Che Tsai. And Dr. Tsai received his bachelor degree from National Jiwon University and the master degree from National Taiwan University in 2020. And he was a research assistant in Academia Sinica Taipei, and now he's a PhD degree student, right, in NTU. And his research interests include embedded systems and intermittent computing. So now please join me in welcoming Dr. Tsai. Okay. Thank you. So please go ahead.
Okay, so let's get started. This is Tsai from Taiwan Academia Sinica. I'm going to introduce our recent work, Intermittent-Aware Distributed Concurrency Control. Our work focuses on the intermittent IoT networks, which are consisted of nodes of batteryless IoT devices. To ensure the sustainability of the IoT nodes, energy harvesting has been proposed as a promising alternative to battery charging. Those batteryless devices benefit from the reduced maintenance cost and are thus more sustainable. But these ambient energy sources are very weak and unstable, so devices in the network suffer from frequent power failure and run intermittently. Such intermittent execution may inhibit task progression. Besides, the smart IoT applications running in a network can perform sensing, computing, and task communication, as well as sharing data and cooperate with each other on different nodes. They may also be executed concurrently to improve the performance. Therefore, to enable concurrent task execution in such network, we not only need to maintain data consistency, but also need to accumulate progress achieved by the devices. An intermittent system usually has an energy harvesting unit which buffers the ambient energy into the energy storage that can support a system operation for a short period of time. As shown in the figure below, the stored energy is discharged when the system is turned on and is charged when the system is turned off. There are other essential hardware components such as the volatile memory, denoted as VM, provides higher performance, but data will be lost during power failures. The non-volatile memory, denoted as NVM, retains the data during power failure, but usually has lower performance than VM. Also, different sensors and connectivity modules such as RF are used for sensing and communication between nodes. Previous efforts has been made to enable a standalone intermittent device to accumulate computation progress while ensuring data consistency across power cycles. Recent work focuses on enabling and improving intermittent communication between two nodes, where both transmitter and the receiver need to be active for at least the airtime for one complete packet. Both hardware-supported and software-assisted approaches are proposed to facilitate packet transmission between intermittent nodes. However, the impact of the intermittency on IoT networking has still received little attention. To observe the impact of intermittency, we conduct an experiment on an intermittent network with distributed tasks sharing remote data. We found that the data unavailability caused by intermittency has a significant impact on the overall computation progress. This is because a task will be blocked when it tries to retrieve data from the offline node. reducing the forward progress achieved by the network. The impact is more adverse when the data access between nodes increases, as tasks tend to be blocked for more times, and when the power becomes weaker. To address the issue, this paper presents the first attempt to address distributed concurrency control in intermittent networks. To increase data availability in an intermittent network, we propose a borrowing-based distributed concurrency control protocol. The main idea is to leverage the existing copies of data objects inherently created in a network to improve data availability. Our method allows 2 versions and 2 copies of one data object. Some of them will be inherently created during task execution. The consistent version is persistently preserved in remote NVM, representing the latest modification. When a task reads the data object from the remote, a duplicated copy is inherently created in the local VM for the consistent version of the data. Upon modification of the data, a working version in local VM is then created from the duplicated copy. And after a task is finished, its working version is inherently saved into local NVM as the modified copy. We allow the tasks to borrow the duplicated copies and the modified copies when the consistent versions of the desired data objects are unavailable, so that the task can still proceed. However, allowing data borrowing raises additional challenges. The first challenge is how to enforce atomicity and durability of the network despite frequent power failures. When a task finished execution, the related consistent versions must be updated in an atomic manner to avoid data corruption. Moreover, the consistent versions scattered on different nodes must be recoverable to a consistent state on each power failure. This is difficult because the nodes may randomly encounter power failures during a distributed recovery procedure, resulting in a non-terminating distributed recovery. The second challenge is how to ensure serializability based on the different data versions and copies. The consistent versions produced by tasks executed concurrently must be the same as if the tasks were executed serially. And this is difficult because allowing tasks to borrow modified copies from other nodes may create implicit task dependency. To solve the challenges, our design principle is to keep the consistent versions always consistent with the progress of the finished task in the network, thus eliminate the distributed recovery to accommodate frequent node failures. This principle is achieved by following mechanisms. First, we use the intermittent 2-phase commit protocol to ensure the finished task commits its modified data accumulatedly into the consistent versions after the participant nodes reach the commit consensus. This ensures the atomicity and durability. Moreover, we propose the distributed validation with task dependency resolution to validate the serializability of a task that may access and borrow data copies from multiple nodes. A task can commit its modified data only if validated as serializable by the network. Thus, the serializability can be enforced. Finally, we have the 2-phase commit procedure incorporate the distributed validation algorithm to reach a consensus across multiple nodes. Our protocol is integrated into a FreeRTOS extended intermittent operating system intended for standalone devices to support intermittent networks. There are 2 main components. The first one is a data manager, which is responsible for accessing desired or borrowable data objects from the network, and is also commit the modified data onto their owners. The second one is the validation handler, who resolves the implicit task dependency and validates task serializability across multiple nodes. The operating system can accommodate power failure and an arbitrary line of code. In our evaluation, we use several MSP430 platforms with the RF transceivers. A power supply is used to generate a range of power sources from stable, strong, to weak. The benchmark application runs on n nodes with 2n tasks, repeatedly to read, write, or commit n+1 shared data objects, while the n can be 3 or 4. There are 3 approaches compared, namely ours, Con, and Sir. Ours is our intermittent-aware distributed concurrency control protocol, while the Con stands for hours without data borrowing. And finally, the Sir is the Con version without task concurrency. The experiment result shows the forward progress under intermittent power has about 20 to 33% improvements by increasing data availability. Especially the improvements are more obvious under weaker power or with more frequent failures, and in a larger network with more copies to borrow from. However, extra overhead is also introduced under stable power, where the forward progress is reduced by 19 to 23% due to the data borrowing regardless of 100% data availability. In the experiment, network scale of our prototype is limited by the available low power transceiver, as larger network suffers from severe collisions due to the hardware limitation. But we believe that the result is sufficient to draw potential extensions. We found that data borrowing incurs extra communication, while data availability incurs ineffective communications. Therefore, an ideal borrowing strategy is able to determine which node to borrow and when, such that extra communications are less than ineffective communications. However, we leave these as our future work. To conclude, to the best of our knowledge, this paper is the first work to address intermittent-aware distributed task concurrency, where we found that data availability can offset the computation progress improved by distributed task concurrency. To address this issue, we propose a protocol to enable data borrowing while guaranteeing data consistency. And we also designed the borrowing-based data management to leverage inherently created data copies. To enable our design, we need to address the following issues. We adopted intermittent two-phase commit to enforce atomicity and durability along with the distributed validation and test dependency to ensure serializability. The experiment result shows the forward progress improved by 20 to 33% with our protocol integrated into an intermittent OS and deployed on a small-scale network. And the operating system for intermittent network is open source, which can be found under a link. Thanks for listening, and I'm happy to take the questions.
Okay, thank you very much. It's really indeed a very solid and very interesting work. Yeah, I'm very impressed. And any question from the audience? Okay, maybe I can raise the first question.
Yes.
The proposed solution is really interesting to duplicate data to improve the progress, but duplicate data introduces extra overheads, and this could increase the complexity for your design to extend to multiple intermittent nodes. Can you have more explanation or more address about how your current work can be extended to multiple nodes? Yeah.
Okay, so we have mentioned that there is a trade-off between there's a communication trade-off between our
Yes.
Our work and the data. So data borrowing incurs extra communications, but data borrowing can also reduce the time of the task being blocked. So we have some heuristic ideas. For example, we can adopt a better strategy to determine when to borrow. For example, if the device is going to run out of power really soon, then it may not be able to run even if it got the data, the borrowed data. So it won't borrow data if it's going out of power really soon. Or another strategy can be only borrowing the data from nearby nodes so as to reduce the communication costs. And
Yes.
to sum up, yeah, the main idea of the strategy is to reduce the cost used on borrowing data and increase the chance of getting the data and keep on running without being blocked.
Yes. I have a follow-up question. Is that because your data is to duplicate, so you include the concurrency control protocol, and
Yes.
For the system that if we increase the number of nodes and the concurrency control protocol, such as two-phase lock-in, and this might seriously affect the progress or the concurrency level of your design. Can you have more explanation about this issue?
Okay, so as mentioned previously, those copies are, sorry, let me find the correct.
Yeah,
Okay.
my question is that to ensure the serializability, and this has some concurrency level overhead, and how to extend your design to multiple nodes. Yeah.
Yes. So first, those data copies are actually inherently created, means that even I don't duplicate it, it already exists in the system, in the network during transmission.
Yes.
Yeah. And our work is to leverage those inherently created data. So we actually are not creating any extra data, but we leverage the existing one. And for the question you asked, if this will increase the overhead for the two-phase lock-in protocol. And here we use a validation-based protocol. So there's no locking on the there's no locks on the data
That's
objects.
a smart idea. That's a smart idea. Okay, thank you very much. Because the time's up, so we need to stop your talk here. Thank you very much. Thank you.
Thanks a lot.
Thank you. So now let's move to our third talk. So our third talk, Dr. Kim, can you share your screen?
Yeah, okay.
Okay, thank you very
Use my
much.
screen. Okay.
Yes, that's great. So let me introduce your talk first. Thank you. So our third talk is entitled PVoT, that is called the Reconfigurable Photovoltaic Array for Indoor Light Energy Powered Batteryless Devices. And the speaker is Dr. Jiwon Kim. And Dr. Kim received his bachelor degree from Ewha Women University, Seoul, South Korea, and she's currently pursuing the PhD degree with Yonsei University. Her current research interests include energy storage management and optimizing energy efficiency for mobile systems. Now, please join me in welcoming Dr. Kim. Thank you. Okay, please go ahead.
Okay, hello everyone. I'm glad to introduce my work, the Configurable Photovoltaic Array for Indoor Light Energy Powered Batteryless Devices. I'm the first Dr. Jiwon Kim from Yonsei University. This talk will be about maximizing the performance of PV array for indoor light energy powered devices. So these days, there is a severe waste problem of disposable batteries. 15 billion batteries are used every year, but only 2% are being recycled. This has created environmental problems, and many companies are looking for the solutions. As a kind of solution, battery is replaced with light energy harvesting for operation, which is expected to greatly reduce the waste. However, in an indoor environment, the demanded energy may not be available depending on the conditions. For example, assume that there is a Tei-Wei remote control with a PV module as shown in the figure on the lower left. If the side where the PV module is installed continues to face the floor, the device may not be able to harvest energy for a long time and may stop working. For this, if PV modules are installed on both sides, the problem may be solved. So to obtain a stable power from the light source, multiple PV modules in different directions are required. A PV array is defined as connected multi-PV modules, and a naively connected PV array is suffering from a problem called shading effect. For example, when two PV modules are connected in parallel, and if one of the module becomes shaded, it will rather consume energy because of the current backflow. So this would lead to the energy loss. In this situation, as shown in the figure below, the configurable PV array can be utilized to increase the harvest power by disconnecting the shaded module. We've experimented the shading effect in various indoor conditions. We first set up 4 PV modules with different harvesting conditions as shown in the figure on the left. And then we measured and compared the harvest energy when 2 of them were connected in parallel. The figure on the right shows the result. As a result, we can see that the harvest energy in some situations were quite lower than using only 1 module due to the shading effect. So this indicates that the shading effects must be handled to maximize the harvesting power. Next, we compared 2 existing methods to address the shading effect of PV array. The first method is using diodes. As shown in the figure on the right, diodes are installed for each PV module and prevent the current backflow. And the second method is using switches. The shaded modules will be switched off by controlling the switches as shown in the figure. We conducted experiment to see the effect of these 2 methods. The figures below show the energy harvested for 60 seconds with the method. As a result, the diode method prevented the shading effect, but it was much less energy efficient than the switch method. The critical problem of the diode method is that the constant anode loss due to the voltage drop is significant even in the absence of the shading effect. This is the big loss just to prevent the shading effect, especially in an indoor environment. So to maximize the harvesting power, we employed the reconfigurable PV array using switches. However, there are 3 challenges that must be solved to exploit the reconfigurable PV arrays in an indoor environment. First, harvesting capability of PV modules should be measured in an energy efficient way. Obtaining the harvesting capability of a PV module requires an open circuit voltage and short circuit current. However, measuring these values in steady state results in high energy loss. Second, harvesting capability should be measured at proper timing. In an indoor environment, harvestable light changes unexpectedly depending on the device movement and light condition. So proper measurement timing is hard to be decided. Third, the optimal switch configuration of a PV array should be found at runtime. However, the calculation of this work is very complex, while the low power indoor IoT devices have limited computing resources. So in this work, we propose PVoT system that maximize the energy efficiency of a reconfigurable PV array for indoor IoT devices. The figure shows the system overview, and PVoT consists of 3 parts. The first part is the photoresistor-based harvesting capability estimation. The photoresistor is a kind of light sensor, and we exploit its physical properties to develop an energy-efficient light sensing technique. And the second part is the event-driven light change detection. PVoT detects irregular light changes in event-driven manner by working with the hardware components in photoresistor block. The last part is modeling the power imbalance threshold. We define a model of power imbalance threshold, which determine the models to be disconnected. This is the details of the first part. PVoT has photoresistor-based sensing block separated from the PV array, so there is no need to make the circuit open or short. A single photoresistor measures the light intensity of a PV group that consists of 1 or more PV modules facing the same direction. And the resistance of the photoresistor is highly dependent on the ambient light, as shown in the figure on the right. So in a dark environment, the photoresistor consumes very little power. By exploiting this property, PVoT designates the photoresistor with the darkest light as a target. And then the MCU goes into sleep mode with target enabled. This process can make the MCU standby for detecting light changes while consuming very little power. So MCU can detect the light changes in event-driven way by repeating 3 steps. As mentioned, after the target photoresistor is designated, the MCU goes into sleep mode. During this time, As shown in the lower left figure, if the ambient light changes, the voltage of photoresistor changes and the interrupt signal occurs with the comparators. This interrupt signal wakes up the MCU. Next, the MCU measures the whole photoresistor sensing values and reconfigure the PV array. After that, the MCU designates a new target photoresistor and goes back into the sleep mode. And the last step, to reconfigure the PV array, the MCU needs to know what is the optimal configuration. However, considering the harvesting capability of every PV module combinations is too complicated, especially for low power MCU with limited computing resources. So to simplify this calculation, we model the power imbalance threshold indicating whether a module should be connected to the PV array. To power imbalance threshold, the power imbalance threshold is modeled using the single diode model, and this is provided in the form of the table or concept. So to evaluate the proposed system, we implemented a hardware prototype hardware as shown in the picture. As PVoT targets energy-constrained indoor IoT devices, we carefully selected low-power components, including ultra-low power MCU. And we first evaluated the effect of our photoresistor-based sensing technique. The baseline we compared to is the existing method that directly measures the voltage and current of PV modules by manipulating the switches. The figure on the lower left shows the energy inefficiency of the existing method. The existing technique measures the open circuit voltage and short circuit current of each PV module one by one. So when the switch state changes, the voltage and current of the PV module fluctuate as the module goes into the transient state and then return to the steady state. So the PV array cannot harvest energy during the measurement, and this leads to the energy loss. Our technique with separated sensing block does not suffer from this problem. On the other hand, the figure on the right side shows the high accuracy of the proposed technique. The baseline technique directly measures the harvesting capabilities of the modules, so it can be considered to be almost ground truth. As shown in the figure, our sensing values are very close to the baseline, so this indicates our sensing values are accurate. And next, we evaluated the effect of proposed light change detection. The existing techniques typically determine the period and measure the harvesting capability periodically. We compared our event-driven measurement to periodic measurements with 3 periods. The figure shows the result in 2 cases. The indoor light changes in irregular pattern, so effective period is dynamically changing. As a result, our event-driven measurement technique is more energy efficient than others under both conditions. Finally, we conducted a case study to demonstrate the effectiveness of PVoT system. The figures on the left show the environmental settings, and we set up the 2 imitated indoor devices with PV arrays and measured the harvested energy for 12 hours. As a result, people showed energy gain in the remote control up to 23.9% in best case. So in conclusion, we observed the energy loss of PV array due to the shading effects in an indoor environment. And we then defined 3 key problems to exploit the PV array for an indoor IoT device. Next, we proposed PVoT system to address the key problems by exploring the physical properties of photoresistors and PV array. And finally, we evaluated the efficiency of the proposed system with the prototype hardware. Thank you for listening.
Okay, thank you very much. Thanks for the interesting and informative work. Any question from the audience? Okay, so let me ask you some questions first. My first question is that the PV array architecture is very interesting, because it enable the harvesting system to measure the PV status and the reconfigure capability. But what's the hardware and the energy overhead on reconfiguring the power of the system? Yeah.
Energy.
Yes.
Okay. Yes. We validated that our energy overhead in the evaluation section in the paper. In short, the energy overhead was very little because the photoresistor in the darkest environment consume power very little power. So we validated our energy overhead very detailed through the detailed experiment. Okay, so that's it.
Yeah. Okay, but for the analysis part, what's the best time and frequency to measure the power and energy for the configuring of the PV?
Actually, when the ambient light changes or device are moved, the best timing of PV configuration is as soon as possible. The light condition is changed. So
I see.
yes.
Okay, thank you. And my final question is that because adapting photoresistors is a very interesting idea, but my question is that is there any other materials that can also achieve the same capability, or it is very hard to achieve that if we don't use the photoresistors? Yeah. Is there any other existing materials? Because photoresistors is a very interesting idea.
Okay. I think there are so many light sensors, but we use the photoresistor because it is two property. It has two property. The varying resistance depending on the ambient light, and it can sense the light. But I don't know what is the
because some others might use the voltage sensor instead of the light with the photos, right? Because they sense the voltage of the capacitor, so they can have some reconfiguring capability. But using the photoresistor is very interesting perspective. Okay. Thank you very much. Because we run out of time, we behind the schedule a little bit, so we need to stop here. Thank you very much for your interesting talk. Thank you.
Thank you.
Thank you. Okay, so now let's move to our last talk. And Professor Chen, can you share your screen? Okay, great.
Hello everyone. Hello everyone, I am Li Jiali from Chongqing University in China. I will present this work for Zheng Rongwei in Shanghai, and Zheng Rongwei will attend us and answer the questions on site. So today I will introduce our fast path for sensor data access on automotive embedded systems named Sentinel. This is the outline of my introduction. Now let's start with the background. As a main information source of domain control units, many new sensors are being equipped in vehicles, such as cameras and lidars. Unlike traditional sensors, this high-throughput sensor generates a huge amount of data. Generally, the sensor data processing flow can be divided into three steps: receiving, preprocessing, and computing. First, the system receives and frees the packets sent by the sensors. Then the system preprocesses the raw sensor data, such as transforming the raw lidar data into point clouds. Finally, the system processes the sensor data via certain algorithms. On the heterogeneous platforms, there are different architectures for data processing. Architecture A is common in host computers, but is impractical for embedded systems for its high demand in processors. The typical architecture after offloading computing is shown in Figure B. Although this architecture breaks the computational bottleneck, the issue of data receiving and preprocessing is still unanswered. The pure hardware accelerator for sensor data processing is shown in Figure C. Through the cooperation between hardware, the participation of the software stack can be avoided as much as possible. However, there is no unified framework to support this implementation. Next, I will introduce the motivation of our work. Processors of embedded platforms are hard to afford the overload caused by the sensor data access. We test the CPU usage when receiving univ packets of different throughputs. The results are shown in the right picture. Obviously, the large throughput leads to significant stress on the embedded processor. To ensure safety, the latency of data paths to processors and the data paths to accelerators need to be considered too. For one thing, the processor needs to perform interrupt handling, network protocol freezing, mode switches, and data copy operations. For another, preprocessing of sensor packets via processors also results in high latency. In order to solve the problem, we propose a novel architecture, Centano, to processing sensor data on automotive embedded systems. This picture shows the architecture of Centano. We try to offload the protocol stacks and the preprocessing drivers in Centano. In this picture, various sensors are data source, and the process or customized accelerators are the end of data paths. We first intend to offload the protocol stacks into hardware, that is, the unified access module, to build the data path to accelerators. We further design the preprocessor module. It's our hardware abstraction for various preprocessing drivers. Centano can build a fast path to sensor data access to processors and accelerators based on these two hardware modules. For the data need to send to processors, we directly map it to processor address space. For the data need to be sent to accelerators, it's directly distributed to the preprocessor module, and then preprocessed data can be sent to accelerators. The unified access module is the center of data access and distribution in Centano. This figure shows the 4 modules it contains. Due to time constraint, I will not introduce them one by one. To build the fast path to accelerators, we abstract the process between the unified access module and the accelerator into a hardware module. The preprocessor modules. The module is used for users to tailor their preprocessing logic according to the drivers. In some scenarios, both preprocessing and computing are performed by processors. Therefore, we do some work at the software layer to take advantage of the unified access module. Similar to sockets, Centano provides several APIs for users. Besides, inspired by the RDMA technique, we implement a zero-copy mechanism. Centano has optimized the data path to processors and accelerators based on the above work. This picture compares the typical data path and the fast path to processors. Centano optimizes the typical data path to processors in 2 ways. First, protocol freezing is uploaded to the unified access module. Second, the CPU copy is avoided. This figure shows the typical data path to accelerators and the fast path in Centano. Centano also optimizes the typical path in 2 ways: protocol offloading and preprocessing offloading. Besides, hardware cooperation shortens the data path and avoids twice CPU copies. We deploy a 69 leader into the frame of Centano as a case study for in-vehicle search. This LiDAR takes the UDP protocol as a data transmission protocol. We use FPGA to implement the unified access module and the preprocessors modules. Now I will give the evaluation of our work. Here is the experimental setup. Now we discuss the CPU usage caused by different access methods in detail. This CPU usage caused by LiDAR data receiving and preprocessing in different implementations is shown in this figure. Compared with the original driver, the modified driver receives the packets through the unified access module. In the pure hardware implementation, the packets are directly sent from the unified access module to the preprocessor module. Compared with the original driver, the CPU usage of the modified driver is reduced by up to 46%, and the CPU usage for data access in the pure hardware implementation is 0. Next, we discuss the latency optimization brought by Centano. Through the hardware protocol stack and the zero copy mechanism, the fast pass to processors would reduce the latency by 59%. Besides, the below table shows the comparisons of the latency produced by the preprocessing function and the hardware preprocessors module. Centano decreased the preprocessing latency of MSOP and DIFOP packets by 93% and 92% respectively. Finally, we compared the latency of an MSOP packet from entering the embedded system to reaching the accelerator. The comparison results show that the latency of the completely offloaded data path is reduced by 93% compared with the original data path. Next is the conclusion of this work. We propose a new design for automotive embedded systems, Centano, which provides fast path to sensor data access to processors and accelerators. We apply Centano to the data access of 16-line LiDAR as a case study. Experiment results show that compared with a typical path for sensor data access, Centano can effectively reduce CPU usage and latencies. So that's all the content of my presentation. Thanks for your listening. And now, please Wei-Ming answer your questions online.
Okay, thank you very much. Okay, is there any question from the audience? Okay, maybe let me ask some few questions. It is interesting to think about the fast path to reduce the software overhead for the transmission latency. And my question is that if you create a faster pace, is there any side effect? For example, it is application dependent, and for each application, do you need to implement your own fast path again? So it is very labor intensive. Can you have more elaboration about this?
Okay, thank you for your question. In fact, we prototype Centano to FPGA, and I think this method can be applied to more scenarios. For example, embedded systems on other like airplanes and other platforms.
Yeah. Okay. Okay. There are two questions online. Let me repeat it here. The first question, the questions are from Dr. Xiaofeng Ding, and the first question is: in the picture showing the data access latency, I see the potential latency. Could you introduce it in detail? And the second question, please answer the first question first. Thank you.
Okay, for the first question, we define the period of delay when sensor data copied to user space is waiting to start processing as the potential latency. For instance, the received data may be sent to another process through the publish subscribe mechanism of ROS. And the data may not be preprocessed until a certain amount is accumulated. Okay.
Okay, thank you. There's another question from the same audience. The second question is that, as far as I know, RDMA technique also implements the zero copy mechanism and protocol stack of loading. Is it suitable for automotive embedded system?
Oh, okay, this is a good question. RDMA is widely used in high-performance computing systems. However, applying RDMA network cards to in-vehicle networks is not ideal. For one thing, devices on both sides need driver support, and for another, RDMA network cards are expensive and difficult to apply them to the actual production of vehicles.
Okay, thank you. Okay, because we have over our time limits, so we need to stop here. Thank you very much. Okay, thank you all from over the world. And now we have finished all the talk here, and now let me announce that our session ends here. Thank you very much. Thank you. Bye-bye.